All right, greetings YouTube, Beautifulmind here, and this serves as our auxiliary or supplementary section for chapter 5. There's a 5.2 star, which is essentially section 5.5 trigonometric equations from this Precalculus the unit circle approach book. All right. So again, this is just an auxiliary section. We're going to be working through trigonometric equations. A few objectives: solve trigonometric equations of the form a sine x minus c equals k, and a cosine x minus c equals k, and a tan x minus c equals k. And then solve trigonometric equations by using the zero product property. Solve trigonometric equations that contain more than one trigonometric function. And then solve trigonometric equations by squaring both sides. Okay. So a trigonometric equation is a conditional equation that contains a trigonometric function with a variable. An identity is an equation that is true for all values in the domain of the variable. Solving a trigonometric equation means finding its solution set, right? So finding all possible values of x that makes the equation true, okay? Yeah. So then solve trigonometric equations of the form t of x equals k, where t of x is one of the 6 trig functions. Step 1, find alpha equals t inverse of x. And write t of x equals to t of alpha, okay? So like that alpha kind of serves as like a temporary either angle or radian measure, right? As a little bit of a precursor, when we go to find these, like we'll have a trig equation, oftentimes there are multiple angles that will work. So the challenge is not only finding one of the correct answers, but finding all of the correct answers. And, we'll incorporate notions where, how sine and cosine repeat every 2 pi radians. So within that 360 degrees, there's going to be at least, usually there's about 2 angles that will work for the equation. And then, when we start working double angle formulas or multiple angle formulas, that'll probably multiply to like 2 or 4 or whatnot. And then, so that's within like 0 to 2 pi radians, and then we can extend it, right? So every time it does a complete revolution on the unit circle, you're going to have another angle. It's going to be a different number, but it'll still make the equation true. So we have ways of capturing all the possible results. So step 1, find alpha equals t inverse of x, and write t of x equals t of alpha. For common angles, find alpha from memory or the table. I think that's the from the unit circle, right? So we'll be referencing the unit circle a lot. Trigonometric function values of some common angles in the textbook. For other angles, use a calculator, right? So again, I think that's referring to the unit circle. If t inverse of k does not exist, the equation t of x equals k has no solution. Okay. So another thing to kind of keep in mind, like when we're doing these inverse trig functions, I think it helps if we're clear about our domain and range off the rip, right? That seems to help to make sure that we're getting solutions that exist, right? Okay, let's see what we got. Step 2, use the table basic trigonometric equations in the textbook to find all solutions of the form t of x equals t of alpha. And then try integer values of n to find all solutions of the equation in the requested interval. Hopefully, I might need to look that up just to have it on file, but we're going to kind of work with what we got for right now. So in this example, we're asked to find all solutions of each equation on the interval from 0 to 2 pi, express all solutions in radians, right? So sometimes I feel like it's easier to kind of conceptual, like usually what I'm doing is working on the unit circle. I tend to work in degrees and then convert to radians at the end, right? Okay, let me give myself some space here. So I'm going to add a page. Okay. Find all solutions of each equation on the interval from 0 to 2 pi. Express all solution in radians. Okay. So I want to start with A. I'm just getting a copy right now. And I'm just going to use this as a reference. So I'm just going to shrink it down a bit. And, ooh, where are you? You are muffled. Listen. Put you like here. Okay. I'm sorry, guys. Give me a moment. All right. I think we're ready to rock and roll. Okay. All right. So let's see. Okay, so root 2 over 2, right? So right now I'm going to spare the unit circle. We know that what sine of 45 degrees gives us root 2 over 2. So sine is like our y value on the unit circle, and our y value is also positive what in quadrant 2. So, right? So we need the quadrant. So the quadrant 1 solution is kind of natural, and then we also need to, basically, if we're going to work in quadrant 2, basically what if we're 45 degrees off the x-axis in quadrant 2, we should also have root 2 over 2. Okay. Let me think. So again, if we're doing this in degrees, we know that what sine of 45 degrees should give us our root 2 over 2, okay? So that's our like quadrant 1 solution. We'll say right now is this. And then sine is also positive in quadrant 2. So for 45 degrees off the x-axis in quadrant 2, what is that? So 180, 140, 135. Okay. Normally to capture all solutions, again, every 360 degrees this repeats. So normally we would say plus n times 360 on both of these guys. But because we only want the solutions from 0 to 360, we don't need that part just yet. And so only other thing I'm going to do is just convert this to radians. And I think this is going to be, let me see. So if we say 45 degrees, I'm going to put it over 1. I'm going to say times my pi over 180. Okay. It's 4, right? So it looks like that's a pi over 4. Okay. And then for this other one, we're going to do what? Pi minus pi over 4. Or we can just convert it like we did this one, right? That'll work too. So like this times pi over 180. Okay. Let me think. We could do that. Let me use my calculator. Right here. Come on. Okay. So let's see. Let's do 135 divided by 180 as a fraction. 3 pi over 4. Okay. Okay. So on the interval from 0 to 2 pi, these should be all the solutions, right? So again, with this being sine is positive, sine is our y value. If we're on a unit circle, all right, our y value is positive in quadrant 1 and 2. So we should have a quadrant 1 solution, quadrant 2 solution. Normally, if we wanted all solutions, we would also tack on this part that says n times 360. So every time we do a complete revolution, we get another result. So integer multiples of 360 degrees. But again, for this specific example, we only want solutions from 0 to 360. So we got 45 and 135, and then we just converted those to radians. And so we got a solution set of pi over 4 and 3 pi over 4. That should be good. Okay. We can at least, so one of the pitfalls is like missing an angle, but at least for the angles that you find, you can at least confirm that these work in the original. So let's just check that real quick. We have our results in radians, so I think we're already in radians, okay? I'm gonna go to my y equals, I'll put sine of x. And I wanna evaluate this when x is, let's do pi over 4. We should get, okay, we're gonna get a decimal. Pi over 4, okay. Let's go ahead and do 3 pi over 4. We should get the same decimal. And then let's just confirm that that is indeed root 2 over 2. We should get the same decimal, okay? All right, so we can be confident in those results from 0 to 360 or 0 to 2 pi. Okay, let's go ahead and try B. I'm gonna copy this. And let's add a page right here. Actually, what I want to do, let's duplicate this instead. Okay. And then okay. All right, so let's try B. Okay. And we'll compare this to our prepared notes momentarily. So for B, we're working with what? Cosine of theta equals a negative root 3 over 2, right? So cosine is our x value. Negative root 3 over 2, okay? And our x value is negative in quadrants 2 and 3, right? So we should have a quadrant 2 solution and a quadrant 3 solution, okay? So now, so that looks like that one of our results from the unit circle, okay? Let's go ahead and do the quadrant 1 portion of the unit circle, right? So we'll just do a rough sketch. A positive x, a positive y, okay? We're considering the quadrant 1 of the unit circle, okay? We have our 3 tick marks. This is like 45 degrees, this is 30 degrees, this is 60 degrees. This corresponds to what? Pi over 6. This is pi over 4. This is pi over 3. This is 90 degrees here. This is pi over 2. 0 degrees and 0 radians. This is what? Corresponds to the order pair 0, 1. This corresponds to the order pair 1, 0. And then we got 3 fractions here, corresponding to each of those tick marks. All the denominators are 2. Okay. And then we count 1, 2, 3, 1, 2, 3. So we go 1, 2, 3, 1, 2, 3. And we take the square root of all the numerators. Okay. So where cosine is root 3 over 2, cosine is our x. So that corresponds, so whenever we're 30 degrees off the x-axis, whether it's in quadrant 1, 2, 3, or 4, that should give us the result of root 3 over 2. But we want the quadrant 2 solution and the quadrant 3 solution, okay? So I think we did it last time, we did it in terms of degrees. So here we see that what? Pi over 6 corresponds to 30. So basically, we just need to be pi over 6 radians off the x-axis in quadrants 2 and 3. So we can say 180, or we can say pi minus pi over 6 and pi plus pi over 6 to get those results, right? So, because x is negative in quadrant 2 and 3, right? So we would do something like our theta here would be pi minus pi over 6. And our theta here would be pi plus pi over 6, right? That way we don't have to do those conversions. Whichever, if you want to do the degrees and then convert at the end, that will be fine as well, right? So then we have 6 over 6 minus 1 over 6 to give us a 5 pi over 6, right? Again, if we didn't have the restriction on the domain, we would say plus 2n pi, right? Every 360 degrees, or in other words, it repeats every 2 pi radians. But because we only want the results from 0 to 2 pi, we're just going to bypass that for now. This should be the quadrant 2 solution. And then the quadrant 3 solution give us 7 pi over 6. Okay? So I got these two results. I'm just going to highlight them. Okay? Should have made a duplicate once it was clear, but that's fine. Let's duplicate one more time. It's starting to knock off the cobwebs. I'm going to keep my unit circle, and I'm going to just get rid of this portion. Okay. Oop. Okay, let's go. Let's just do it like this. Okay. All right. So then for C, all right, so we have what? Tan of x equals a negative root 3. Okay. So tan is what? Sine over cosine. Okay, which angle, like if we're in quadrant 1, right, it looks like this is going to be, quadrant 2 and 4. Okay, but let's work on quadrant 1. So if tan is sine over cosine, which is our y over our x, it looks like that corresponds to 60 degrees, right? If we say, so tan is 60 degrees, and we did our y over our x, all right, we'll get a result of root 3. So it looks like whenever we're 60 degrees off the x-axis, and in any quadrant, when we take the tan of 60, we should get a result of root 3 over 2, but tan is going to be negative in quadrants 2 and quadrants 4, all right? So it should be a quadrant 2 solution and a quadrant 4 solution. So quadrant 2 and a quadrant 4, okay? So we said whenever we're 60 degrees off the x-axis. So the radian measure there is going to be what? Pi over 3. So if we want to be in quadrant 2, what we'll do, we're going to say pi minus pi over 3. That should give us the quadrant 2 solution. And we can say, if we want the quadrant 4 solution from 0 to 2 pi, we can do, oh, I just realized something. I forgot to identify my domain and range. Hopefully that, well, we should probably check these results before we move forward. Let me check this real quick. So I didn't do my domain and range, but let's just check real quick. So this one, we did cosine of theta, so I'll just drop down and do cosine of x, okay? And then, so I want to call on that function. Oh, not that one. Number 2, okay. We want to evaluate this when x is, let's try 5 pi over 6. We should get some negative decimal, okay? We're going to confirm that that works momentarily. And then let's try 7 pi over 6. Okay, we should get the same. And then let's confirm that that corresponds to a negative root 3 over 2. Negative square root, come on, of 3 over 2, like this. Okay, so we're good there. I think an additional step that we should incorporate, just be clear about your domain and range, because sometimes we'll produce results that are outside of our domain, and you know, or at least check to make sure that these are working. Okay, so we said we need to be what, 60 degrees off the x-axis in quadrants 2 and 4. So for the quadrant 2 solution, we're going to say what, pi minus pi over 3, all right? And then for the quadrant 4 solution, we're going to say 2 pi minus pi over 3, right? 60 degrees off the x-axis in quadrant 4 from 0 to 2 pi. Okay. Okay, now one other thing, maybe here we probably should incorporate the all solutions here because tan repeats every pi radians instead of every 180 degrees instead of 360 degrees. So I am going to go ahead and include it here just in case we get multiple results other than these one that we're capturing from 0 to 2 pi. Okay. So this x is going to take on the form 3 over 3 minus 1 over 3 to give us 2 pi over 3. Okay. And that's going to repeat. So we're going to say plus every n pi radians. Okay. We're just going to check to see if we get any multiples in there that we making sure we're not missing any. And then this other solution, it's going to be 6 over 3 minus 1 over 3 to give us 5 pi over 3. Again, we're going to tack on this plus n pi radians. Again, it repeats every 180 degrees. So then we want to test a few values like integers, right? Let me see. If n were 0, we're just trying to capture all the results from 0 to pi, 0 to 2 pi. Let me see. If n is 0, we get this result. If n is a 1, we get 5 pi over 3, which we got from the other one. And I think honestly, it's just the first two that we have, right? So it didn't come into play here. So like for instance, when n is 0, we get 2 pi over 3. When n is 1, we get 5 pi over 3. If n is 2, now we're outside of our range. We could try when n is like a negative 1, but I think that also gets us out of our range. I think the results here, I'm just gonna go with 2 pi over 3 and 5 pi over 3. Okay. Okay. So when we did it, we got these results. So now let's compare these to our prepared notes. All right. Let's compare this to the textbook. Okay. Let me back up real quick. Come on. Pi over 4 and 3 pi over 4. Pi over 4 and 3 pi over 4. I just want to check our results before we dive a little deeper. 5 pi over 6 and 7 pi over 6. 5 pi over 6. Okay. And then the last one's 2 pi over 3 and 5 pi over 3. Okay. So let's just kind of dive a little deeper into the way the textbook did it. So the solution set on the interval, okay, so for A, right? The sine of x equals root 2 over 2. So arc sine is going to be pi over 4. Again, we got that from the unit circle, okay? So then the sine of x is going to equal to the sine of pi over 4. So then step 2. So then to capture all the solutions, normally we would do pi over 4. Again, sine repeats every 360 degrees or every 2 pi radians. So to capture all the repeats, we would tack on that's plus 2n pi. And then for the quadrant, let me see, sine is our y. Y is what? Positive in quadrants 1 and 2. So for the quadrant 2 solution, we would say pi minus pi over 4 plus 2n pi, right? And then if we want the solution set on the interval from 0 to 2 pi, when n is 0, we get this. I think if you let n be 1, any of the repeats are outside of our 0 to 2 pi. So that's why that was the result. Okay. Okay, let's do it like this. So cosine of theta, this is where we started. From the unit circle, we got 5 pi over 6, right? So then to capture all the repeats, again, cosine repeats every 360 degrees or every 2 pi radians. So we tack on this 2n pi, right? Okay, that would capture all the repeats. And then, so since we're working with cosine is our x. X is positive in quadrants 1 and 4. So if we want the quadrant 4 solution, we're going to say the 360 minus 5 pi over 6 or 2 pi minus 5 pi over 6. That'll put us in quadrant 4, right? And then we got this. And then it really, for this one, again, because our domain is restricted from 0 to 2 pi, it really only takes effect when n is 0. So we only get these two results, right? We're going to see some examples where that higher values of n are going to generate more solutions, right? But the main takeaway is being cognizant of these repeating results, right? And how to capture them, okay? So we got that same result. And then a similar, okay, so for tan, I think it's what, 60 degrees or pi over 3 radians. Tan is negative in quadrants 2 and 4. It's a similar argument though, pretty much. Okay. All right. When n is 0, okay, so we can't do when n is 0, right? Because it gives us something outside of our restriction. So I think we just did 60 degrees, right? We knew it was pi over 3. We knew it corresponded to 60 degrees. Again, we got our result from the unit circle, which was this guy from the unit circle. And then it really should have been the negative pi over 3, but again, we were just using a different technique, and I knew we were going to get to the same result. But then to capture all the repeats, right? Because the restriction on tan is what, from negative 90 to 90. That's why they went with this result. And then to capture the repeats, we tack on this n pi, because tan repeats every 180 degrees or every pi radians. So then when n is 0, we can't use that result because the domain was restricted from 0 to 2 pi. But then if we let n be 1, we get the result we generated. And then when n is 2, we get the other result that we generated, right? So they kind of did theirs a little bit different. Let's just kind of work some more examples to kind of make sure that what we're doing is proper. Let's keep going. Okay. So here we're asked to find all solutions. Sine of x equals 0.3, round solutions to the nearest tenth of a degree, right? So they said they want the result in degrees. We're going to have to use our calculator. Okay. So then our alpha would be what? Arcsine of 0.3. Let's go ahead and identify our restrictions from way back, a few sections back. If we think about sine, right, we have to restrict the domain of sine from negative 90 to 90. So if we're doing degrees, negative 90 degrees to 90 degrees, right? So it can pass the horizontal line test. Normally this would be our x and this would be our y, negative 1 to 1, right? But then when we go to take arctan, this is going to be our x and this is now our y. Okay, so this is what we did in previous sections. So then when we go to do the arcsine of 0.3, we should get a result between negative 90 to 90. Let me see if sine is 0, 0. Let's just, so we have to use our calculator. Okay. And again, sine is what? Positive. Sine is our y value. So we should have a quadrant 1 solution and a quadrant 2 solution. Again, there should be a quadrant 1 solution and a quadrant 2 solution. All solutions, okay. So then let's go mode and put it in degrees. Okay. Let's do the arcsine of 0.3. Okay. So 17 degrees, that should be our quadrant 1 solution. So we got x equals, or is approximately, to the nearest tenth, so 17.5. And again, this is going to repeat every 360 degrees, so we're going to tack on this plus 360 in degrees. All right, so every integer multiple of 360. And then for quadrant 2, we need to be 17.5 degrees off the x-axis in quadrant 2. So we're going to capture that by saying 180 minus 17 to generate that quadrant 2 solution. So the other one is approximately, so we're going to say 180 minus that answer. Okay, so we're getting 162.5. And again, it repeats every 360, so we're going to tack on this plus 360 in degrees, okay? Integer multiples of 360. round solution to find all solutions. So this should be all the solutions, right? And then where n is going to be any integer, right? And so we can test it. Let me think. Okay. So we'll go to my y equals. So sine is the first one. So I'm just going to call on that function. All right, so let's let n be 0. So if n is 0, it'll just be 17.5. And we should get something close to 0.3, right, because of the rounding. And then let's try the 162.5. Same, okay. And then we can do integer multiples of 360, right? I mean, I'm not going to check those because, But again, you can let n be like 1, 2, 3, -3. Any integer that you want, because it goes on forever. Let's see. That's about the best I can do. Okay, so we got these results. Let's compare this to the prepared notes. Okay, use arcsine function to find arcsine of 0.3 is 17.5 degrees. So sine of x equals the sine of 17.5 degrees. All solutions are going to be given by, again, I think in the solutions they forgot to put the 1. 17.5 degrees plus n times 360 degrees is fine. And then the quadrant 2 solution was the 180, right? With the 162. And I think that's it. So you see the result here. And you see the result here for any integer n. Okay. All right, let's see what else we got. So find all solutions of this guy on the interval from 0 to 2 pi. Okay, so we're working cotan, right? All right, I'm starting to forget a lot of the properties. Let me think. So one thing with cotan, let me see. So let's take some notes here. Let me start with tan of x, right? The restriction on the domain, tan, passes through the origin. So that domain was restricted from a negative pi over 2 to pi over 2, right? And the range was restricted was all reals, right? Okay. So then if we consider cotan of x, we have to shift that by 90, so add pi over 2. So now our domain is restricted from 0 to pi. And our range is all reals. So now when we go to investigate arctan, why am I drawing a blank there? Yeah. Come on. Get back. Thank you. When we go to investigate arctan, these guys switch places, right? Our domain is now all reals, and our output we should get results from 0 to 180 or 0 to pi, right? So that's my domain. We just want to make sure that that's there and in place. So when we do inverse or arccotan, okay, let's go ahead and put that in our calculator to make sure that we get a result between 0 to pi. Okay. Now for cotan, let me think about this. Cofunction. So okay, so if we I'm going to use where cotan should be the same as what? 90 tan of 90 minus x. That's the cofunction property. I think that's how that goes. Yeah, right? Cofunction property. Hopefully I'm remembering that properly. So cotan of x should be tan of, in this case, it'll be pi over 2 minus x. Cofunction property. So instead of, I'm going to, and we want arc cotan. Okay. Okay. So tan of pi over 2 minus x should equal this negative 3.5, okay? So then when we go to do arctan, and I know there was a more direct way. I might have to look that one up because it was something like, you should be able to do like 1 over, I'm just drawing a blank, but I'm gonna just kind of continue with this train of thought. I know where it is in my notes if I go look for it. I'm just trying to avoid that. But let me see. So when we do arc tan, our result needs to be between negative 90 to 90. Let me try arc tan of this guy, and just to see what happens. So arc tan, we need to be in radians. Had a lot of moving parts. Negative 3.5, okay. We do arc tan. Okay. So what is pi over 2? Let me crunch that number. Pi over 2. Okay, I think it's within range. Because we would have a negative 1.5, and so that looks like it's within range. Okay. Okay, so I'm getting pi over 2 minus x is approximately, says, I think it's supposed to be a 4. 4 decimal places, 5708. No. 2925. 2925 radians. Okay. Add and add. So then x is going to be approximately, let me see. I want to say pi over 2 plus that number. Okay. Let me go like this real quick. Okay. I want to say negative of that answer plus pi over 2. Okay. Okay, we're going to check this. 8633. Okay. And again, we should tack on plus n pi radians. So let's just do that real quick. Plus n pi radians. Okay. So then again, let's kind of check these numbers to see if we can get a confirmation. Okay. Cotan. Ugh. Okay, so 1 over cotan, right? I feel like we made a mistake somewhere. Too many moving parts, right? So cotan of x equals this. So that means what? Tan of x should be equal to, we use the cofunction property. We could have also done cotan of x is going to be the same as what? 1 over tan. All right. If we have cotan of x equals a negative 3.5, let me think about that. So is that going to be the same as, so then tan of x should equal 1 over a negative 1 over 3.5, right? All right, let's see if that works. So let me think. Dang, it's cotan of x equals this. So then what? In terms of tan, cotan is 1 over x. Okay, so let's do this. Let's do this. This is why I'm kind of going in circles, right? So right here, cotan of x, right? But that's going to be the same as 1 over the tan of x. And that should equal a negative 3.5. So then when we do our calculation, tan of x should equal a negative 1 over 3.5. Okay, so let's just work with that. Okay. So now we're working with tan of our result should give us a negative 1 over 3.5. Okay. So let's see if that works. Tan, we need our number back. Okay, let's see if I can get this in one go. Back up a couple of spaces. That one, right? Okay. So then if arctan of that gives us this, we want the positive, dang, I'm losing track. And then plus pi over 2, there it is. Add. Okay. Okay, let me think, add. Okay, so what I'm trying to do is, like, if we do this pi over 2, it should be, I'm just going to do minus the arctan of a negative 3.5. I'm trying to get this 2.8633 in one go. Okay, we got it. So now, okay. So if we say tan of that result, we should get a negative 1 over 3.5. So if I do tan of that answer, we get something like this. I don't know about that. Let's see. Negative 1 over 3.5. Okay. That's about the best we can do. I know it's a little bit, and then the, integer multiples of pi. That one's not too terribly bad. Let's find all solutions of this on the interval from 0 to 2 pi. Okay. Let me see. What if we let n be a negative 1? All right, let me get back to that result. Not that one. I think it's this one. Okay. So now, what if we say that answer? Matter of fact, I'm going to store this as alpha A just so I can have it on file. So then, if we want 0 to 2 pi, can we subtract pi? Can we subtract 2 pi from that? Let me see that alpha A minus 2 pi. I just want to see what the number is. Okay, we got a negative, so we're good there. We're going to ignore that one. But then let's take that number alpha A minus pi. We still get a negative there. So when n is 0 is the first one, so we got the 2.86. And then let's do when n is a 1. So we're going to take that number A plus pi. All right. What's 2 pi? All right. So it looks like we get this 2.8633 and this 6.0049. Those are the results that we're getting. $8,633. And we're also getting this 6.0049. Okay, so we got these results. Okay. Let's compare it to our prepared notes and we'll get to the bottom of it. Let's see what's going on here. So most calculators do not have a cotangent, so if cotan equals this, so then, okay, they turned it into a fraction. That makes more sense. Tan of x equals a negative 2 over 7, right? Which is essentially what we got. Okay. So then our alpha, they got this negative. At one point, I know we got that. Let's keep going. Okay. So then they get this negative 0.2783 plus integer multiples of pi. So for n is 1, 2.8633, and we got those numbers, all right? So theirs was a lot cleaner than what we experienced, but, we eventually got there. Let's So one thing off the rip, they rewrote cotan and tan. We ended up using the cofunction property. I think that made it a little bit worse. So what they did, they used the reciprocal property, right? Cotan equals a negative 3.5. So if cotan is 1 over tan, right? So then our tan is going to be equal to a negative 2 over 7. So then you work it from there. So you rewrite cotan in terms of tan. Again, they just flipped both sides. First, they wrote the negative 3.5 as a fraction. If cotan equals this, that means tan equals this. That's fine. So then you just flip it. That's much easier to work with. We were using cofunction. That made it more challenging, so that's fine. So then our alpha, our result should have been from negative pi over 2 to pi over 2. You know, we ended up getting this, or they got this, but, you know, we got to the bottom of it. Okay. And then once you have your x, then you tack on that integer multiples of pi, so plus n pi. And then once you have that, then you like just kind of test, do different values of n to make, and just find all the solutions in your interval from 0 to 2 pi. And they ended up getting the exact same thing that we got. Okay, let's try another one. Let's just try another one. All right. Let's just try another one. Find all solutions of this equation. Now we got a double angle formula here, right? Okay, so we'll work it. Find all solutions of this on the interval from 0 to 2 pi. Okay. So we're starting with what? Cosine of 2x equals a half. Okay. So I'm going to do a substitution method. I'm going to say something like I'm just going to say let theta be 2 pi, and just work in terms of theta, all right? So then if we say what? Cosine, just to try to simplify this a bit, cosine of theta equals a half. Can we get that from the unit circle? So then theta, cosine of what angle gives us a half? Cosine is our x value, is at 60 degrees. We want it in terms of radians. So what, pi over 3 radians? Okay, so it looks like our theta equals pi over 3 radians. Cosine is our x. X is positive in quadrants 1 and 4. Okay, so this we're going to say plus n times 360 degrees. That's the quadrant 1 solution. And I'll kind of work over here. For the quadrant 4 solution, that's like 60 degrees. So we want to be 60 degrees off the x-axis in quadrant 4. So then for the quadrant 4, what we'll do is say theta equals, we're going to say 2 pi minus pi over 3. So that's 6 over 3 minus 1 over 3 to give us 5 pi over 3, okay? And again, that's going to repeat. Oh, why am I doing degrees? That needs to be plus 2n pi radians, right? Right here. That needs to be 2n pi radians. Again, plus 2n pi radians, okay? So again, every 360 it repeats. So we got our quadrant 1, quadrant 2. But then now, what we need to do is back substitute for the theta, the substitution that we did, right? So our theta was 2x. So then from quadrant 1, now we have 2x equals pi over 3 plus 2n pi. And then from quadrant 4, we get what? 2x equals 5 pi over 3 plus 2n pi. Okay. Yeah, let's keep going, right? I think we're good. Let's keep going. Okay, so now if we go to solve for x, we multiply both sides by a half. And so in this guy, we get x equals pi over 6 plus n pi radians, okay? And then from this guy, if we multiply both sides by a half, 5 pi over 6 plus n pi radians. So then now only thing that's left, we need to play around with like multiple values, because we only went from 0 to 2 pi, right? So we need to kind of test the integer multiples of pi and extract all solutions that are from 0 to pi. So for instance, I just have this urge to let n be a -1 first, just to make sure we're outside of our range. Okay. So if we get a negative result, then we're going to scrap it. 1/6 minus 6/6, that's going to be negative, right? So we won't have to do that. Okay, when n is 0, we're getting what? Pi/6. If n is a 1, looks like we're getting our 5. Okay, let's keep going. 1/6 plus 6/6 to give us 7 pi/6. Is that right? Okay, I think we're good. Let me clean it up a bit. 7, that's supposed to be 7 pi/6, okay. I think that's it from that one. And then if n is 0, we get a 5 pi/6. And then if n is a 1, 6 plus 5 is 11 pi/6, okay. And I'm just going to put these in ascending order, just rearrange their order. Like this guy here. 1, 5, 7. Right. So because it was a double angle formula, we got 2 additional results from our usual 2. Okay, before we compare it with the textbook, let's check these results in our calculator. Okay. So what I'm going to do, I'm going to go here to my y equals. We got what? Cosine of 2x. We're in radians. Cosine of 2x. Okay, I'm going to quit and make sure I'm in radians, okay? So then now what I'd like to do is call on that function. I'm going to evaluate that function. Let's first try pi/6. Okay, and a half is correct. Let's try 5 pi/6. Should get the same thing. And then 7 pi/6. And lastly, 11 pi/6. Okay. Okay, I feel pretty good about these. So it's coming together. I know it's a little dicey along the way, but I think we're working out our kinks, all right? And it seems like it's coming together. Okay, let's see, how did we do? Okay, so step 1, your alpha equals arc cosine of a half is pi/3. I think we got that same result. Pi/3, see the blue theta equals pi/3. So cosine of 2x equals cosine of pi/3. So find all solutions from the table. So if we have 2x equals pi/3 plus 2n pi, we had that, right? You can see it in blue in the middle of the screen. 2x equals pi/3 plus 2n pi, right? Gives us, so we multiply both sides by a half. Pi/6 equals, okay, we got that. 5 pi plus n pi. We got all these results, and when n is -1, we get a negative result, right? So we would scrap that one, but when n is 0, pi/6 is good. And I think 13 pi/6 is outside of 2 pi, so we would not use that one. It should just be the 4, right? The 4 in the middle. Same thing we got. So the values resulting from -1 are too small, and those resulting where n is 2 are too large. So the solutions correspond to 0 and 1 are these 4 guys, which is the 4 that we got. That was an adventure. Let's try another one. It's coming together. I think it's coming together. All right. Find all solutions of this equation. Okay, so now we got to incorporate some trig identities. Okay. Let me think. Okay. So it looks like we can try u substitution here. All right. Let's just try u substitution. Okay. So what I'm going to do is say something like let u equal sine of theta. Okay. So if we account for that, right, we're going to have what? 2u squared minus 5u plus 2 equals 0, right? So then it's factoring. We're looking for what? Two numbers that multiply to give us 4 and add to give us -5, right? We have to say our a times our c. This is our a, this is our times our c. When our leading coefficient is not a 1, you know, we work it a little bit different, right? So two numbers that multiply to give us 4 and add to give us -5, -4 and -1, right? Okay, so what I'm gonna do is rewrite that -5 using the 4 and the 1. So we got this 2u squared minus 4u minus 1u plus 2, right? So then I'm going to do factor by grouping. Okay, you could also do box method here, but this is just how it's coming out for me right now. The first two we can factor. We're doing factor by grouping. So whenever you have 4 more terms you want to factor, you do factor by grouping. So then the first two, it looks like we can factor out a 2u. It's going to leave us with a u minus 2. So if we factor out a negative from the second two, it should leave us with also another u minus 2. Again, we factored out a negative. So then using the zero factor property, we can factor out the u minus 2, and we're going to be left with 2u minus 1. Okay, so then by the zero factor property, u equals 2 or u equals 1/2. Okay, so let's back substitute. So if u equals that, so then sine of theta, it looks like equals 2. Let me, sine of theta and sine of theta equals 2 or equals 1/2. So the half, we can get that from the unit circle, right? And isn't the 2 outside of our, let's check real quick. So if we think about our restrictions, like when we go to take arc cosine, right, we got to think about our restrictions. Normally we restrict the domain of sine from where? Are we doing in radians? So we restrict sine from where? Negative pi over 2 to pi over 2, like this. And then the output is normally what? -1 to 1. When we go to take, undo. Okay. So I'm just going to move you here. These essentially swap places when we go to take the arc sine. Okay. So right here, because 2, when we go to take the arc sine of 2, 2 is outside of our domain. So no solution. So for this guy on the left, I would say no solution for that guy, because the 2 is outside the domain of sine, right? So I don't know if you remember when we first introduced the arc trigonometric or the inverse trigonometric functions. I was like, usually when we're doing that, we want to be clear about our domain and range. This little part we have in orange, it just comes in handy, right? So I just usually when I'm doing my inverse trig functions, I just try to have that orange part ready to go. So that was from an earlier discussion. Okay, so this guy on the right, from the unit circle, sine is like our y. Find all solutions, okay? So sine is our y, 1, 2, 3, 1. So we're talking about 30 degrees off the x-axis. If y is positive, so there should be a quadrant 1 solution and a quadrant 2 solution. All right, again, there should be a quadrant 1 solution, a quadrant 2 solution. Sine is our y, 1, 2, 3, 1. Again, we should be what, 30 degrees off the x-axis in quadrants 1 and 2. 30 degrees corresponds to pi over 6, okay? So then quadrant 1 should be theta equals what? Pi over 6, and it repeats every 360 degrees. So plus 2n pi radians. And then the quadrant 2 solution, so we're going to say what, 180 minus pi over 6, or in other words, pi minus pi over 6. And then we're going to say tack on this plus 2n pi radians, okay? So this guy persists, this guy. So 6 over 6 minus 1 over 6 to give us 5 pi over 6 plus 2n pi radians, okay? Let me kind of want to shrink those guys down. Oop, undo. I want to duplicate this guy. Okay, these are the two. Let me undo one more time. One more time. I'm going to duplicate this. All right, so these are the results that we got. And let me try to expand them as best I can, just because we're so short on space. Let me get rid of this. Nope. Delete. And duplicate. And expand. Okay. And again, the results that we got are these guys. Okay. All right, so radians, okay. Let's check this on our own as best we can. We could try multiple powers of n. I'm probably just gonna do when n is 0. Honestly, I'm just gonna use my prepared notes. I feel pretty good about this. Let's see how do we do. We got pi over 6 and 5 pi over 6. Okay. So factor, so we get pi over 6 and 5 pi over 6. No solution for the sine of theta equals 2 because sine of theta is not between -1 to 1, right? So I think we get that same thing. So then to capture all, we should tack on a plus 2n pi radians to both of those guys. Oh, we only want 0 to 2 pi? No, why are they doing this? Let me see. Are the only two solutions on the interval from 0 to 2 pi? Since it has a period of 2 pi, the solutions are going to be pi over 6 plus 2n pi and 5 pi over 6 plus 2n pi for any integer n. Yep, we got the same thing. Woohoo! Okay, let's try another one, all right? Practice makes what? Absolutely not. Hopefully you're not saying perfect, right? Practice makes improvement, all right? Okay, anyway. All right, let's, again, I don't know if it was a student that shared this with me or my old martial arts instructor, but he would say things like, whoever it was, I can't remember who, but they were like, and I think it was my martial arts instructor. And I think I had students that actually would invoke this thing. But you don't want to practice something until you get it right. You want to practice it so many times that you can't get it wrong, right? Obviously, I still need to do some more practice, but that's why I appreciate this, because it makes me think. It's something that I don't normally do. So that's why I like it, because it gives me a chance to practice. And, I don't really see myself just doing it for the sake of doing it. Now, if I was working on a project or something that incorporated it, that's where I think it brings it to life, right? Like, I feel like the challenge with a lot of these things is that they're kind of abstract and they're not like relevant. But if you were using this for some project that you were working on to advance something, to advance whatever, to get closer to some goal that you're working towards, then it brings this stuff to life. And this stuff has like endless applications, especially in this technological age with drones and, all sorts of things, trajectories and, coding. I mean, it's everywhere. But yeah, so I feel like if you all were using this towards something that you're interested in, it'll be a lot more relevant, And I'm sharing this because I recently came across this story where this teacher, I think it was a high school teacher, somewhere in New York, I think in the past 10 to 20 years, somewhere in that range. So this is 2026. But he would allow his students to skip class to pursue their own interests. And he won like Teacher of the Year like 3 times or something like that. Because it was basically talking about that the students felt like, when would I use this? This isn't relevant. And so, it was a total disconnect. But then when you allow people, and honestly, if I had a school, I would probably mimic this notion. But he was like, if you allow people to pursue their interests and is relevant, it's something that it's helping them move towards their interests, then it's not abstract, it's more concrete, it's more relevant, and it's assimilated a lot better. So at some point I will build that. It's kind of like this movie called Accept It. Anyway, let me Accept It. It's a funny movie, it's a comedy, but it's kind of built on that notion. It's a funny movie, you get a chance to watch it. It's from it's an old movie though. Maybe the 90s or early 2000s, something like that. Okay, anywho. All right, let's look at this one. Find all solutions of this equation on an interval from 0 to 2 pi. Okay. All right, so let's use the trig property for sine. So let's see. So sine squared, because we have what? Sine squared plus cosine squared equals 1. So I'm going to rewrite this 1 minus cosine squared theta, okay, minus cosine theta minus 1 equals 0, okay. Let's expand this out and see what happens. I also have this urge to multiply both sides by -1. But let me expand it first. So we'll get this 2 minus 2 cosine squared theta cosine theta minus 1 equals 0. Okay. 2 minus 1 is a 1. That's a plus 1. So I'm gonna multiply both sides by a negative. Right. So then and combine like terms. So that'll be a 2 cosine squared theta plus cosine of theta. That was a plus 1, now it's a minus 1 equals 0. Okay. So then it looks like a repeat of the previous, right? I'm going to bypass the substitution method and see, can I just factor it directly? Or we could say let u equals cosine of theta and then proceed in that fashion. We should have at least one of these two, so 2 cosine theta and then another cosine theta. One should be positive and one should be negative. And it should be a 1 and a 1, right? So then we just need to straighten out our signs. Let's just try this. If that doesn't work, we're going to reverse those signs. Let me do a quick check. So first, outer minus 2. So let's reverse the signs. Let's make this guy plus. And now let's try it. So first, outer, and then inner. So you have 2 cosine theta minus cosine theta to give you a 1 cosine theta, and then minus 1. All right. Okay. So I think we're good there. Okay. So then from here, cosine of theta equals a half, or cosine of theta pi over 2. I think we're okay with this number. Yeah. Let's keep that number. So from the unit circle, right? Cosine of what angle? Cosine is our x. Cosine of what angle gives us a half? 60 degrees corresponds to pi over 3. So cosine is positive. We should have what? Our x value is positive. We should have a quadrant 1 and a quadrant 4 solution for that first part. Let me, again, we should have a quadrant 1 and a quadrant 4 solution. Okay. So the quadrant 1 is what? Pi over 3. So then we say something like theta equals pi over 3. And it repeats every 2n pi radians. Okay. And then quadrant 4, it's really what? Negative, we said what, 60 degrees off the x-axis in quadrant 4. It's really a negative pi over 3, right? So I'm going to write it as negative pi over 3 plus 2n pi radians, okay? So we got these results for that first one. And then cosine is our x is a -1. That's a quadrantal result, right? Or on the axis at what, -pi. Yeah, I think we just get one result there. So we got this theta, looks like it's a -pi. And that's going to repeat every 360, so plus 2 in pi radians, or every 2 pi radians. Okay, so we got 3 different thetas that we need to test on the interval from 0 to pi, okay? Now, if we let n be a -1, what is that? That's 2 over 1, 6 over 3. So it's going to give us a negative result. So I don't think the -1 works for any of these guys, okay? When n is 0, okay, looks like we are getting a pi over 3. That negative result, we're going to bypass that one and bypass that one, okay? So now let's do when n is a 1. When n is 1, that first one goes outside of our range. The second one, we're going to say 2 pi minus a negative, it's going to be 2 pi minus pi over 3, right? So 2 over 1, 6 over 3 minus 1 over 3 to give us a 5 pi over 3, okay? So 5 pi over 3, okay? Also when n is 1, so 2 pi minus 1 pi is just pi, okay? And then I think when n is 2, none of these work. They all go outside of the range. So we're getting these 3 results. All right, I think when n is 2, they all are too big. Okay, so let's at least check these results. Hopefully we didn't miss any. I don't think we missed any. We didn't have any like weird double angles or anything like that. So let's just check this in our calculator before we compare it to our prepared notes. Okay. All right, so I'm clear. I'm going to go to my y equals. We're going to do 2 times the sine of x quantity squared. That should work. Minus cosine of x, okay. We should be in radians, okay. Then I'd like to call up, I forgot something, -1 right here, okay. So then I want to call on that function. I want to evaluate that function when x is a pi over 3. We should get 0, okay. And then let's test 5 pi over 3. Okay, and then let's just test pi. Okay, that's about the best we can do there. Okay, let's compare this to our prepared notes. So find our solution. Use the Pythagorean identity to rewrite this. So they did the same thing we did. Sine squared becomes 1 minus cosine squared. And then you can see the line where they multiply by a negative. We got the same thing. Multiply both sides by -1. We got this. Then it factors into this. Okay. So cosine of theta is a half, which is pi over 3, or -1. We get these. When n is 0, we get these results. And this one. All of the values of n result in solutions outside the interval from 0 to 2 pi. So then we get these results. Same thing we got. Okay. All right. We're almost there. I know it's kind of dragging on. We're almost there, though. We only got 5 more slides. I think it's like 2 or 3 examples. Find all solutions on the interval from here for cosine. Okay. Cofunction. Do we need to use the cofunction property here? What happens if we square both sides? Let's try squaring both sides and see what happens, all right? So, let me do this. We got the square root of 3 times the cosine of x equals the sine of x plus 1. I'm going to say this squared and this squared, and let's just see what happens. Now on the left, looks like we get 3 times cosine squared x. On the right, sine squared x, 2 sine x plus 1, okay? Now cosine squared, let's use the trig property. So cosine is going to be what? 1 minus sine squared x. Okay. Distribute that 3. We're going to have 3 minus 3 sine squared x equals all this stuff here on the right. I'll keep working over here. Actually, this is slide 30. I want to duplicate this guy. Okay. And I'm going to get rid of the beginning part. And just pick up where we left off, which is this guy. Matter of fact, we don't need this anymore either. That'll give us more space. Okay, that's where we left off. We're going to set it to 0, so I'm going to move everything to the right-hand side. So that's going to give us 4 sine squared x plus 2 sine x minus 2 equals 0. Okay. So it looks like we can factor out a 2 from everything. That's going to give us 2 sine squared x plus sine x minus 1 equals 0. Right, divide everything by 2. This looks similar to what we had before. Okay. We want to try to factor this. We know we're going to have a 2 sine x and a sine x here. This has to be a 1 and a 1. I think last time we said this was a minus and a plus. Let's just see if this works. So first times first, outer times outer, inner times inner, last times last. This looks good, right? So then from here, zero factor property, sine of x equals what, a half, or sine of x equals negative 1. This looks like a repeat, or similar to what we were just doing a moment ago. So for instance, where we have sine of x equals a half, we can get that from the unit circle. Unit circle, sine is our y, 1, 2, 3, 1. So we're 30 degrees off the x-axis in quadrant 1. Let me see, 0 to 2 pi, okay. So our y value is positive, and there should be a quadrant 1 solution and a quadrant 2 solution. So again, there should be a quadrant 1 solution and a quadrant 2 solution. Okay, sine is our y, 1, 2, 3, 1. So 30 degrees, I guess we're in terms of radians, right? Let me check. Yeah, radians. So 30 degrees corresponds to pi over 6. That's going to repeat so we're going to say plus 2 in pi radians. And then in quadrant 2, so we can do pi minus pi over 6. Plus 2 in pi radians. So that'll capture our quadrant 2 solution. And then we need to go back. So sine is our y value. Our y value is equal to negative 1. That radian measure is 3 pi over 2, right? So then we got this third one, x equals 3 pi over 2, okay, radians. Because it's basically the negative y-axis. And if we just want 0 to 2 pi, for a similar argument as before, it should be, so I'm just going to write the results. It should be pi over 6. So 6 over 6 minus 1 over 6 to give us 5 pi over 6. And then we got a 3 pi over 2. All right, we got these results, okay? I'm just going to compare this to my prepared notes. We've been at this for a while, so I don't know about you guys, but I'm a little bit exhausted, okay? All right, 1, 5, and 3 pi over 2. Let's see, how do we do? And again, we could check it in the original. Let me see. Oh, what am I hitting? Okay. So if we wanted to check, we could say the left minus the right, and then we should get a result of 0. I'm just gonna look at the prepared notes. I'm tired. Find all solutions. So square both sides. Okay. Yada yada yada. 2 sine of x minus 1. So pi over 6 and 5 pi over 6, and then 3 pi over 2. Pi over 6, 5 pi over 6, and 3 pi over 2. Other values of n result in solutions outside the interval from 0 to 2 pi. Oh, check. Oh, they got us. I knew that was going to happen, right? Something was like, check it anyway. So the solution set is only the 1 pi and the 3 pi over 2. And I started to check. I was just being lazy. I was so tired. They got me, right? So the 5 pi over 6. If we try to check that in the original, it does not make it true, all right? So, wait a minute. Let me see. Yeah, right? If we tried to check it, we wouldn't get a result. We wouldn't get a true statement. So we honestly should scrap that 5 pi over 6. I'm just going to backtrack and just strike through it. If I were in a testing environment, I would definitely check it. For here, I just, like I said, I got tired. I didn't bother checking it. So that 5 pi over 6 is what's called an extraneous solution, right? It's the algebra is fine, but then when we check it in the original, it doesn't work out. So we should have checked it. So don't be lazy, all right? Okay, that was an adventure. Yeah. Okay. And let me add a page. Let me go ahead and do that in my instructor notes as well. Let me back up real quick. Blank instructor notes. This one. I think everything else was fine. I'm going to add a page here. Okay. All right. So let me just do a brief recap. Some takeaways. So the trig equations, they get a little dicey. They're not trivial. So some things are like whenever we're finding the inverse trig functions, sometimes it helps if you're clear about your domain and range to identify those extraneous solutions. As we saw in the last example, when we get our final answer, just check it, right? Just check all your results, right? Just plug them into the original. Because sometimes we produce what's called extraneous solutions, where the algebra or the trigonometry is correct, but we produce results that are outside of our domain. So when we try to plug them back into the original, they don't work. So we have to scrap them. What are some other takeaways? Practice, right? Exposure, collaboration. So, I'm available. Working with your classmates or somebody that gets it, a tutor. You got AI at your disposal. You have a lot of tools to get it. Just do your best. Just try and, just do the best you can. Try to get to the bottom of everything and things of that nature, okay? Let me see if there's anything else. And then we were doing a lot of factoring. It was another main takeaway. The multiples, right? So once we had our quadrant 1 solution, and then we had to figure out in what other quadrants, the tan and cotan stuff, where we had the reciprocal properties. The first time we did it, we used the cofunction property. You can try it. If that's getting to be too much, then try the reciprocal properties for tan and cotan. We're working with those. Like if you have to do a cotan example. Write big if you still plenty of space. We got to find all the repeats, right? So it's either quadrant 1. We were using the unit circle a lot. So we had either quadrant 1 and 2 solutions or quadrant 1 and 4 solutions. When we were working with tan, it was either like 1 and 3 or 2 and 4. And then tacking on those the periods, right? So for sine and cosine, they repeat every 360 degrees. So we were tacking on either the n times 360 degrees or the 2n pi radians, right, to capture all the repeats, things of that nature. So a lot of moving parts. It takes practice, exposure, confidence, determination. Just keep trying, keep trying. If you feel yourself getting bogged down, put it down for like an hour or two. Eat something, go do some exercise, take a nap. My recommendation is to tackle this when you first wake up. I tend to wake up in like the middle of the night. That's usually when I'm doing this kind of stuff. That's when my mind is the most fresh, most clear. It's quiet, the least amount of distractions. Everybody's asleep. And just try and then do what you can on your own and then try to seek out help, okay? All right, gentlemen. And with that, we're going to go ahead and end the session here. And from one beautiful mind to another, take care and peace.